We are going to be getting our calculators out and doing some sums as we calculate the energies of photons, as well as see how much energy is needed for an electron to leave the atom. And as always, pause the video so you can download the PDF. This time it's one PDF for all the HL electronic configuration stuff. So today we will be doing these first 3 points, and then in the next video we'll cover these points 4 and 5. Okay, so let's get started with linking ionization energy to convergence limit. So during the SL content, we have seen that the shells get closer together as they get further away from the nucleus. So we can see these shells here are a lot closer compared to here. So so this is n equals 1 all the way up to n equals 7. So as they're getting closer together, if we can remember, this means they are converging. So converging is just a fancy way of saying they're getting closer together. And then after the 7th shell, so after the last shell, the gap is so small that there's no gap at all. So if there was an 8th shell, which there isn't, if there was an 8th shell and we drew it in, the gap just wouldn't be there. So when everything converges together so much that there's no longer a gap, this is called the convergence limit. So just past the 7th shell, immediately past the 7th shell, this is called the convergent limit. So the convergent limit is when electrons stop existing at fixed energy levels. So we can imagine an electron climbing a ladder. On the atomic scale, we could have an electron here, or here, or here, or here. But the electron is never in the middle, so we could never get an electron here. But after the convergence limit, you can get electrons sort of like slowly kind of moving between the rungs. The same as when you climb a ladder. So if you're very small, you don't start up here, and then you can't appear over here. So when you climb a ladder, you do slowly make your way up. So so you can't disappear and then reappear. So this is the same as electrons. Once you've gone past the convergent limit, then they can be anywhere on the ladder. They can have any energy. All right, so back to the quantum world. So what we already know is that you can excite electrons with photons. So if we have an electron here, you can excite it with a photon and it ends up in a higher energy level. And then when it goes back down, a photon is emitted. And the emitted photons give us our emission spectra. But if you give this electron too much energy, if you give it too much energy, then it goes greater than the convergence limit, then the electron has no shell to go into, so then the electron has therefore left the atom. So when an atom loses an electron, there are more positive protons than negative electrons, resulting in the atom having a positive charge. So we can just do a quick calculation. So if we use sodium, so sodium has, so if we do the pen calculations that we've done in the past, so sodium has 11 positive protons, 11 negative electrons. We don't really care about the neutrons. But if it's lost an electron, we have the sodium ion. So the sodium ion still has 11 positive protons, because it has to have 11 because it's sodium. And it has 10 negative electrons. So plus 11 minus 10 gives us a +1 charge overall. So anything with a charge is called an ion. And because of all of this, because all of this can be measured, so it is known exactly how much energy it is needed to remove an electron from an atom. So it is known how much energy is needed for the electron to be removed from an atom. This leads us to our first of many definitions. So we're going to have quite a lot of definitions like this throughout the course. And definitions like this are usually per mole. So this gives us our ionization energy. And the ionization energy is the energy required to remove 1 mole of electrons from 1 mole of an element in the gaseous state. So here we go. So this is just like the generic equation here. But we could use beryllium as an example. So if we're going to do it for a specific element, So beryllium, yeah, has to be in the gaseous state. Becomes the beryllium ion, also in the gaseous state, plus an electron. Okay, so now on to the calculation. So like I said, we're going to be doing some calculations so we can figure out exactly what the convergence limit is. And if you know the convergence limit, you can then figure out the ionization energy. So here we are. So calculating convergence limits and photon energy. So we've got three equations here, and then an explanation of what's going on down at the bottom. So yeah, so E is the energy of the photon, H is Planck's constant, and this is in the data booklet, and that is a fixed value each time. Then yeah, F is frequency of light, C is speed of light, again this is a constant, and yeah, this is in the data booklet. Lambda, so this is a Greek letter, is wavelength of light, and that's measured in meters. And then our final thing, if we're ever trying to convert like one thing into a mole of things, then yeah, we need Avogadro's constant, and again another constant also in the data booklet. So yeah, these three numbers you don't need to remember, you'll find them in the data booklet. So yeah, so this first equation here is just like the connection between the energy of a photon and the frequency of light that it has, and then yeah, it's connected via Planck's constant. Then this equation is the connection between the speed of light. So the speed of light is a fixed value, and that equals the wavelength multiplied by the frequency. So if one goes up, then the other has to go down, or if that goes down, then this has to go up. So that kind of is, yeah, the link between those two. And then this final equation here is connecting these two equations together. So if you want to know the energy of a photon, but you've only got the wavelength of the light, then you can use this equation. It basically is just rearranging for F and then substituting what F equals, yeah, over here. Nice and simple. So we're going to do a quick practice question now. So yeah, if the frequency of light of the convergence limit for hydrogen is 3.28 times 10 to the 15 hertz, calculate the ionization energy of hydrogen in kilojoules per mole. So first equation we need to use is this one. This is going to give us the energy of one photon. So yeah, Planck's constant, just get double check, so yeah, 6.63 times 10 minus 34. We're multiplying that by the frequency, what we got in the question, so 3.28 times 10 to 15. Calculator time, 6.63 to the minus 34, 3.28 to the 15, so yeah, 2.17. So yeah, just going to three significant figures, as that's what we've got in the question, times 10 to the power of minus 18, and then yeah, as it's an energy, it's in joules. So whenever you do calculations, you always want to be checking the numbers, do they make sense? So this is a very small number, which is what we want, because yeah, photons only have a very small amount of energy. So to now convert this into per mole, this is when we use Avogadro's constant. So just double check we have Avogadro's constant. So 10 to the minus 18 times 6.02 times 23. Use the calculator properly. Okay, so this is going to give us a very big number, and I'm just going to divide it by 1,000 straight away, because this is the that's give us the answer in joules, but we want the answer in kilojoules. So yeah, this is a nicer number to write down. So 1,309 kilojoules per mole. Okay, nice and straightforward. That you can see there, hopefully. Okay, so let's move on to what affects ionization energy. So we have three things. So atomic radius, nuclear charge, and the shielding effect. So with each of these, you need to remember that the negative electrons are electrostatically attracted to the positive nucleus. And it is always going to be the outer shell electron, so the highest energy electron, that is removed first. So what we're talking about here is the first ionization energy, the energy required to remove the first electron. So we have an analogy to help us. So to help us think about this, we are going to use the age-old classic that I'm sure you've seen in loads of cartoons from the past, but probably not. The age-old classic of a lovely bunch of sausages and a dog. So dogs are classically very much attracted to a lovely bunch of sausages. So the sausages are, of course, the nucleus, and then the outermost electron is, of course, the dog. So we've also got this in our diagram here. Sausages for the nucleus, dog as the outer shell electron. Okay, so on to our first point. So as atomic radius increases, the ionization energy decreases. So atomic radius is probably the easiest one to picture. But as you go down the group, the number of shells is also increasing. So everything in period 1 has 1 shell, everything in period 2 has 2 shells, all the way up to 7. So as the atoms get bigger, the outer shell electron is just physically further away from the nucleus. So the electrostatic attraction is weaker. So with a dog, the further away it is from the sausages, the less likely it will go after them. So less energy is needed to move the dog away from the sausages. So let's have a look at our example here. So lithium is in period 2. Our little nucleus is in. So lithium is period 2, so it's got 2 shells. So this gap is, it's just physically smaller because the outer shell electron is on the edge. So that gap is just physically smaller when we compare it to, like cesium down at the bottom. So it's got more shells. This is just a much bigger gap. So therefore, less energy is required to remove that electron. This electron, is less electrostatically attracted to the nucleus. Okay, so now let's have a look at nuclear charge. So as the number of positive protons increase, the ionization energy also increases. So to help us with this, we're going to compare lithium to fluorine. So with both elements, the first electron is always going to be removed from the same shell. This is from n equals 2. But lithium only has 3 positive protons compared to the 9 of fluorine. So this only has 3 positive protons compared to the 9 of fluorine. So fluorine's nucleus has a greater hold over its outer shell electrons. So the gap's pretty much the same. But here, for lithium, this electron is only feeling like a +3 effect. Whereas, it's the same gap, but all of these electrons are feeling a +9 effect. So more energy is needed to remove fluorine's outer shell electrons. So going back to the dog analogy, with more sausages, the more the dog wants them, so more energy is needed to move the dog away from that bigger pile of sausages. Okay, so on to our final thing, so the shielding effect. So the inner shell electrons shield and therefore reduce the nuclear charge experienced by the outer electrons. So this is when the electrons in the inner shells provide a neutralizing effect. So they partially neutralize the positive pulling power of the nucleus. So the outer shell electrons, therefore are shielded from the attraction to the nucleus. So this can give us the idea of the effect of this can give us the idea of effective nuclear charge, which is the attractive force experienced by that valence electrons. So again, we can use lithium and fluorine as an example. So lithium still has 3 positive protons, and fluorine still has 9 positive protons. Now let's have a look at the effective nuclear charge. So both have 2 inner electrons. So we can -2, -2. So the effective nuclear charge for lithium is +1. If we look at it for fluorine, it's going to be +7. So with lithium, this electron is just feeling a +1 charge from the nucleus, whereas each electron in fluorine is feeling an attraction of +7. So yeah, just go through that one more time. So yeah, we can see that the outer shell electron of lithium can only feel +1. And then yeah, again, comparing that to fluorine, its effective nuclear charge is +7. So yeah, so the shielding effect also helps explain some links to the periodic table. So the shielding effect explains why the ionization energy going across the period also increases. So we're going to go into more detail for that in the next video. And yeah, and this is because as electrons in the same shell can't shield each other. So all of these electrons here, even though there's more of them in this shell, they can't shield each other. So the effective nuclear charge increases across the period. So each electron is feeling a stronger electrostatic attraction to the nucleus as you go across the period. So going back to the dog is going to find it harder to smell the sausages if there are lots of other dogs in the way. Maybe, I don't know, I'm no dog expert. Alright, so there we go. That is all from this video. But in the next one, we're going to go into more detail about linking trends of the first ionization energy to the periodic table, as well as how ionization energy data support the idea of sublevels. And if you have enjoyed this video and want more IB chemistry content, then please do like, subscribe, tell all your friends who are in your chemistry class. And if you want one-to-one tutoring from me, then check out my website. Catch you in the next one.